Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. We will pick it up exactly the point where we left the discussion in the last class. We were discussing the classic Wheatwater-Strand paleoplacer deposit of gold and uranium in South Africa. It's a case of a classic placer deposit which was developed by 5 to 6 major rivers, and the provenance was the gold bearing quartz lode deposits in the nearby cratonic area, and it is also unique in the sense that it is also a major resource of uranium. There has been significant enrichment of uranium in the form of detrital uraninite along with gold, and there are zones where towards the southern part uranium dominates over gold, and in the northern part gold dominates over uranium, and it is a deposit which is Archean in age, old deposit. So, as it happens with all the old deposits, the ideas about the origin of these deposits will always be debated. There are features which will be indicating origin in a mechanism which would otherwise look different from the well accepted placer model, mechanical concentration model. The situation is that the gold grains here, they retain their detrital characteristics along with the indicating transportation, longer distance transportation, along with the detrital quartz grains constituting the conglomerate bed, and the localization of enriched mineralization at the contacts whenever there is a older unconformity erosional surface. And the evidence of the placer model also comes from the fact that gold has been transported as dominantly detrital grain rather than being dissolved in some fluid and getting enriched in this deposit, because of the believed reducing condition of the Archean atmosphere, where gold was not soluble in the crustal fluid. It requires an oxidizing fluid for its transport in the fluid medium, and so is uraninite, which also cannot get transported in the fluid in a soluble +6 form, and that is how we believe the detrital model. And there is little indications of this deposit being metamorphosed to any higher grade rather than simple a very low grade density species metamorphism, and which possibly would not be efficient enough to mobilize the fluid, although we haven't. So, the alternate model which have been proposed by many workers, which is the hydrothermal model for this origin of this deposit, we will defer the discussion till the time that we discuss about the nature of hydrothermal fluid and what hydrothermal fluid are. But for the time being, we finish off the discussion of this particular deposit with the fact that there has been alternate model of hydrothermal origin for mineralization of gold and uranium in this deposit. So, with this, let us move over to the situations where we could see some of the very recent placer deposits which are of mechanical concentration origin. So, here there is the cenozoic placer systems. One is the Otago region in South Island, New Zealand, which is the area where which the sediments have been derived from the Otago schist belt, where there are some gold deposits, and this Otago region in South Island, New Zealand, is one of the recent examples of very young placer deposits of gold. In the Ballarat Goldfield, Victoria, Australia, it's also a gold only deposit of mechanical concentration origin. It's also a placer. Here on this right side, we what is shown here is the Orange River system in South Africa, and this is Namibia, this is the Botswana, where it is also very well known for its diamond potential, and this area which is area is drained by the Orange River. All those which are shown with the diamond symbol are generally the areas which having diamond deposits in the form of the kimberlitic diamond, kimberlite pipes, and we could see that this is an ideal situation where this Orange River, which is formed as an offshore diamond concentration here, as a very recent example of a of a placer system of diamond. This is also essentially fluvial, although the deposition has like in case of or rather unlike in the case of Wheatwater Strand, where the deposition has been more on the fluvio-deltaic part of the system. Here some of the deposition has been taken place in the near shore offshore region, where it is also driven by the eddy currents, and this is one example where we can see a mechanical concentration process which has been operating and giving rise to diamond deposits of placer origin. As we know that placer deposits could also be originated by the waves, by the tides waves that we see in the littoral region in the or the beach region or the shelf region in the seas, world ocean. The only situation is that whether the beach placers would be different from the way we have dealt with the for the fluvial placers or not. Mechanism wise, it's difficult that the beach placers should be having any kind of a settling type of sorting here, because of the very narrow and a very turbulent, very energetic conditions prevailing there in the Schwarz region. Entrainment also looks to be unlikely, but all depends on the local conditions of the tide and its energy, where in some of the beaches it is believed that there is some amount of entrainment mechanism which also works. Then with this kind of situation, we mostly would be explaining the concentration or the sorting of this particle, or the enrichment of this high density material in the form of placer by shear and by transportation sorting kind of mechanism, which I will not be discussing in much in details here. Examples of beach placers: we get a huge accumulation of minerals like monazite, which is essentially a primary source of the metal thorium, which is very essential for generation of nuclear energy. And the example is the eastern coast of India, where we get lots of such occurrences, enrichment of which we call them as the beach placers or monazite bearing sand deposits all along the different selected area in the east coast. And it of course will very much depend on the availability of such kind of provenance or such kind of rocks which will have the concentration of these heavier minerals, and that's how it is subjected to a situation where we have the appropriate provenance. It's all about the fluvial of the system, the fluvial placer, the alluvial placer, and the beach placers. We will not be discussing any there are not many areas where you get distinct placers of aeolian origin. So we will not be discussing that here. Now we will be switching over to another important process, which is also an exogenous process, driven the energy being provided by sun, and this process is essentially the process of enrichment. We call this process as residual concentration process. Essentially, it's a process which is arising out of the differential leaching of constituents from the rocks, leaving behind the constituent which will be useful to us. So, for example, this is a cartoon which shows it's an original rock. Let's say it's of a granitic composition which contains silica, alumina, sodium, calcium, potassium, magnesium, and other major oxides. And this particular rock is subjected to the weathering condition on the surface, and the physicochemical conditions will be such that other than aluminum and a little bit of iron, most other constituents, silica, the alkali, will be leached out from the rock, so that we are left with a residue which is enriched with respect to aluminum. So, such kind of residual concentration process have been in operation, and they are all the recent phenomena, quaternary deposits which are being worked out in many different parts of the world. There is one of the very good examples, Indian examples, which we will be discussing in details. That is the east coast bauxite all along the eastern coast of India. So, the preconditions that we have is that the rock should be rich in alumina, and also the concentrations of silica should be low, and the situation is favored by proper topographic and climatic parameters. Generally, we observe that these kind of weathering processes are more facilitated in humid tropical kind of climate, where this weathering and the dissolution of many of the elemental oxide species is favored and is efficiently done by the fluid, which essentially is the meteoric fluid which precipitates on the surface and then interacts with the rock, and as would be obvious here, the such kind of residual concentration process will be very much dependent on the nature of the surface of the rock. If it should have enough of surface area available for the interaction of the fluid with the rock. So, that means if a rock with a good fracture density in the superficial region, which would allow efficient population of the meteoric fluid, will always be a better host to give rise to such deposit than a rock which is unfractured or not providing any porosity or permeability for the meteoric fluid to percolate. Now, if you want to understand the process, then we have to get into a little bit of fundamentals, little bit about the behavior of elemental oxide like silica and alumina. Here we are considering silica and alumina because the constituent, the silica, is the one which we essentially would like to be removed from the rock, so that the rock becomes richer in alumina. And it's this kind of deposit, this kind of process, which is, we call them as the residual concentration process, generally gives rise to deposits of aluminum, and most of the world production of aluminum comes from such kind of deposits, which are the residual concentration deposit. And similar to a very familiar process that we see in many parts, which are the laterites, is essentially is a lateritization process by which a rock gets converted into a rock richer in aluminum and iron, giving it a very typical texture, which generally we see as laterite. We call them as a piezoelectric texture, and as and when the conditions are conducive and are favorable, when there is substantial enrichment alumina in them, they give rise to the bauxite, and even we call them as lateritic bauxite. So here we see the antipathetic relationship between the two important species like silica and alumina. Alumina is, as we all know, it's amphoteric in its characteristic. Its solubility increases both in the alkaline and the acidic conditions and passes through minima at around a pH of just about 6, near about 6, where it passes through the minima. So it would indicate that anywhere we get such kind of a fluid where the alumina will be insoluble and silica will be soluble, then that will be a situation where that will be the most favorable condition for getting a rock enriched with respect to alumina. And one more important thing is that the topographic factor is also an important one, because since we need the components like the alkali, magnesium, silicon, all to be dissolved in the meteoric water and to be out of the system or to leave the system, not to be reprecipitated in any form. So that means we need to have a good favorable topography for this process to operate efficiently. And so let's look at this diagram, which is an EH-PH diagram, which we discussed in the context of iron deposits in the previous class. There is also the, as it shown, is the lower and the upper limit of pH and EH in natural aqueous environment, and also holds good for the surface. And in this diagram, without getting into further much of the complicated details, this is an EH-PH diagram on which this thick line, thick curve is the curve for iso or equal solubility of both aluminum and iron. So if the condition on anywhere on the surface is near to this thick line, then we are unlikely to get any rock to be enriched with respect to aluminum. It will only be giving rise to a rock where the alumina and iron will be of equal proportion, and that will not be a material which we will be calling as the ore of bauxite. The area which is in lighter gray is essentially the area in which aluminum is more insoluble, and as we just have seen, pH at around about 6, where the aluminum is most insoluble, and we can get the bauxite formation on corresponding to this kind of EH and pH, especially the field which is marked as 6 in this diagram. In contrast to that, if we look at any other field, for example, in this particular region anywhere, we will get aluminum as more soluble. So the aluminum will dissolve and will be out of the system, and we won't be able to have any bauxite deposit formed there. So the outcome of this process of residual concentration is the formation of the bauxite ore. In fact, the bauxite or the lateritization is a process. It is said that any crustal, any rock which is exposed on the surface can be lateritized. It just meets the appropriate combination of the physical and the chemical environment. Even a rock like basalt, which contains very less amount of silica compared to rocks which are a granitic rock where the silica is more, can also be lateritized, and there are examples, Indian examples, where basaltic rocks were enriched by this process to give bauxite deposits. Some central Indian examples are there, we will discuss them. And any rock which is aluminum rich, for example, we have the vast tract of the sillimanite bearing sillimanite and garnet bearing quartzofelspathic gneissic rock in the Eastern Ghats belt, which are known as the Khondalites. They have been the important major source rock from which the massive east coast bauxite deposits formed. So these bauxites definitely would be could possibly be classified or could be distinguished on the basis of the kind of source rock from where they are derived, and also they exhibit different type of structure and texture. Most situations where we get the bauxite is the surface blanket, where, or we can call them in the highland laterite or highland or the lateritic bauxite, which forms from common rocks. Here the mineral is gibbsitic. So what we actually call as bauxite is essentially mineralogically is a combination or is a mixture of hydroxides of aluminum. If it's AlOH3, it's gibbsite. The alpha or gamma form of AlOH or AlOL, those basically the diaspore bohemite. So the one which we call as the bauxite ore is a combination of these aluminum hydrated oxides of aluminum. And one thing with respect to this diagram also we should remember that it's virtually not quite possible to get a rock or a bauxite which will be absolutely free of iron, which is containing a concentration of iron to 0. Invariably the bauxite will have some amount of iron in it. So the hydrated oxide of iron, which is a limonite kind of material, are also there in the bauxite ore. So the surface blanket we find it's more gibbsitic, rests directly on the parent rock with the parent rock texture preserved, and it's controlled by the joint pattern in the rock. We get bauxites in interlayered beds, lenses in stratigraphic sequence, bauxites on volcanic domes, where the bauxite is piezolytic and mineralogically it is bohemitic. There are pocket deposits in limestones. They are essentially the karst type of bauxite which form in the cavities, solution cavities that are formed in the limestone because of dissolution phenomena, and they are later on deposited by clay material, aluminous rich material, and where we also get bauxite formed in that. Pockets of deposit of limestones, clay or igneous rocks, these are structureless, more gibbsitic to piezolytic. We also sometimes get detrital bauxite, means the bauxites which have been transported from a previous enriched bauxitic ore, which are basically sedimentary or they reworked. And essentially we understand this process to be a residual concentration process through the interaction of surface fluid with rock under favorable physical and chemical parameters. But there are also possibilities. People believe that in many of the areas where there are rich bauxite deposits, they actually result from the continentally derived wind blown dust, which gets converted to bauxite. We cannot discuss much on their exact mechanism because it's not known, but we at least can understand through this process by using simple EHPH diagram and mutual solubility of the species like silica, alumina and iron. Here are some of the pictures. This is a typical look of a bauxite as to what we call as the small hemispherical or semispherical mass, which is here are the piezolites, and they range in size in few millimeters to centimeters, sometimes larger. So this is a typical look of a bauxitic ore which is derived as a highland bauxite with piezolytic texture. This is another example of a bauxite ore where we can see it's more iron bearing. This is a typical bauxite sample from a karst bauxite in Ural in Russia, and this is also contains mostly bohemite as the aluminum mineral, and it has some of the iron minerals as limonite. This is a typical look of the bauxitic ores. Even they sometimes look almost like which are called as the bauxitic dewey crusts, sometimes form as almost like a layer, brick looking kind of a layer on the host rock, which one of the examples is the East Coast bauxite, for which they were not been able to be identified for a good amount of time. Well, so this process that we are essentially considering are the processes which are processes of essentially enrichment, means from an existing rock like a aluminous rock like a granite or a condylite, this material being converted to bauxite. And we also, as we discussed when we were dealing with the iron deposits of sedimentary origin, we discussed that what we see as the primary ores in the form of the layered banded hematite jasper or banded hematite quartzite, there actually the concentration or the content in terms of iron will be always fall short of what can be called as an high grade ore, going to up to 55 or 68% of iron oxide. Here this is a good example, it is taken from one of the iron mine. It's what we see is these are the banded iron formation, and it has formed the enriched iron enriched part, almost similar to what we get in case of residual concentration. So iron deposits also can get enriched to high grade from the low grade parent material, and in the process where we have to have a situation where there will be enhanced solubility of the silica which is present in the cryptocrystalline form, colloidal form as jasper. They have to be selectively leached out of the material, giving rise to the high grade ore. This lateritization process is also is an important process after it was observed that some of the terrains where there are some primary gold mineralization in some proximity, close proximity or in some distance, the lateritization process also enriches, or the laterites also contain some gold in few parts per million. In some areas of the world, they are also being worked out for gold. After that, the economic importance of this laterite also went up. The other important metal which also is enriched in the process of residual concentration is nickel, and the source rock are the ultramafic rocks. In fact, these resources of nickel in the as the residual concentration is even higher than what are available in the form of the nickeliferous sulfide deposits in the ultramafic rocks. So essentially, the minerals in the ultramafic rocks, the olivine, mainly the olivine and the pyroxene, they contain nickel in their structure, and when they are exposed, these are acted upon by the surface processes and get converted to the ferromagnesian minerals like olivine get serpentinized, and this serpentine, after a further process of enrichment, gives rise to horizons where the nickel is trapped. This is a typical profile of nickeliferous, we can say nickeliferous laterite. The zone which will be having a iron crust, followed by a piezolytic lateritic kind of zone, then will be followed by red limonite and yellow limonite, and then we'll have the ore within boulders, and this is the zone which is labeled as garnierite. Garnierite is essentially a name which is a generic name given to the nickeliferous clay minerals which are derived through the process of alteration and hydration of the origin, the primary ferromagnesian minerals like olivine, and finally when they in the deeper part where the fresh rock is exposed, or you get the fresh rock. And if you take the nickel concentration, then the nickel concentration here will be low within this top part, which will be defined by the pedolith plus. So essentially pedolith, the term is, it denotes the soil, top soil layer, and the saprolith is the layer which actually indicates the more rock like characteristics, where this is the saprolith zone, which is the one which is more enriched, and the zone in which you get the concentration of nickel trapped in the nickeliferous clay minerals, which are the garnierite. And if you look at this profile, the nickel concentration has a high in these zones where we have the ore within the boulders, the garnierite and the rocky ore, and again falls back to normal background value when you reach the basement rock or the host rock. And in this situation we see that chromium, aluminum and iron will always decrease in this particular region. They will have the minimum value because this region is the ore or the nickel can be extracted where the nickel can attain concentration of the order of even 1 to 2%, and the silicon and magnesium will also be increasing in this zone because they are leached out from the surface and deposited here within this region. And so where we get the clay, which are essentially aluminosilicates and clay, hydrated aluminum silicates. So that's how we get the zone here. So these are the examples of a surface operated process, an exogenous process which gives rise to rich ore deposits of important metals like aluminum and sometimes even nickel and gold. And also if we consider that enrichment of the primary iron ore to give rise to the high grade ores by selective leaching of silica, that also can be included in this process, although these do not come under the strict process of sedimentary process, but they are surface operated process. So we will continue discussing about this. Thank you.